So, about the second topic, which is about the waves and the properties of the waves. So, the general properties of the waves or a wave motion. So, basically, what happened? It's a way by which energy transfer from one place to another. A wave transmit energy from one place to another. Example: energy carried by the water wave generated by the boat, or for example, if you drop a stone into a pond. So if this stone is thrown into a pond, what will it will produce? It will produce ripples or waves. So basically, the energy from the stone is transferred from one place to another, carried by the waves. So there are two main types of waves. Which one? One is longitudinal, another one is transverse. The transverse wave, a wave in which the particle vibrates perpendicular to direction of the wave, we call that as a transverse wave. For example, as you can see in this picture, if we consider the particle, so if you consider this particle, you can see the particles are moving up and down. And what happened to energy? The energy actually travels from one place to another. So vibration of the particle is perpendicular or 90-degree to the direction of the wave. This kind of wave is known as transverse wave. Whereas if the direction of the particle, the movement of the particle is parallel to the direction of the wave, we call that is opposite, that is known as longitudinal wave. Some examples of the transverse wave like water waves and all electromagnetic waves. All electromagnetic wave means wave which does not require a medium or can travel through vacuum. These are known as electromagnetic waves. They all are transverse, which include radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma. For transverse wave, the maximum point is refers to the crest and the lowest point are known as the troughs, and the distance between the two successive crests or two successive troughs, that is known as the wavelength, and the distance from mean position to the extreme position, that is known as amplitude. So the amplitude of a wave is the maximum displacement of a wave from its rest position, where wavelength is a successive the distance between the two successive crests or two successive troughs, or length of one wave, like one complete wave. When we draw, this is a one complete wave, so length of this one complete wave is known as wavelength. What is a longitudinal wave? A wave in which the particles vibrate parallel to the direction of the wave. We call that as longitudinal. So, example, you can see these are the air particles which are disturbed due to the cone of a loudspeaker. So when the cone is vibrating, it causes the vibration of the air particle. So these air particles are moving or vibrating to and fro and transfer energy from one place to another. The region where these particles are very close to each other, in that region the pressure is high, we call that as a compression. And the region where the particles are away from each other, we call that region as rarefaction. In this one, the vibration of the particle is parallel to the direction of the wave. Same thing, you can see a variation of the pressure if we sketch a graph to show how the pressure vary. So as the particles are close, the pressure is high, and when the particles are away, the pressure is low. So in the rarefaction, the particles experience a low pressure, where in compression, the particle experience a high pressure. So whenever longitudinal wave travel from one place to another, it produces a pattern of compression and rarefaction. This is another illustration of how a sound is a longitudinal, so how it travels from one place to another. So you have a tuning fork. When this tuning fork vibrate, it disturbs the air molecules. So these air molecules also vibrate and transfer the energy from one place to another. So region where these air particles or air molecules are closer, we call compression, and region where they are away, we call rarefaction. The distance between the two successive compressions. So if we take a distance between the two successive compression, this is one compression, this is another. So the distance or the length between them is known as wavelength, which is denoted by lambda. And identical, the line which represent the identical points of different waves, we call that as wavefront. So this red line is actually showing a wavefront. Wavefront means it is showing the identical positions, identical way the particles are vibrating. So this is one wavefront, this is another wavefront, and distance between the two successive wavefront is also known as wavelength. So region where the particles are closer, compression, particles are away, rarefaction, and distance between them is known as wavelength. And when the air particles are vibrating, they are vibrating to and fro, and the direction of the vibration of these particles is parallel to the direction of the wave. So compression is a region where the particles are closer and the pressure is high, where rarefaction is a region where the particles are away and the pressure is low. The frequency means how many vibrations are there in 1 second. Number of vibration in 1 second, that is refers to frequency. Example, so as you can see, the particles are disturbed and the water is going up and down. So water is the medium which is transferring energy from one place to another. Now, the term frequency means how many vibrations are there in 1 second. So you have a 10-second timer. As you can see in the figure, 10-second timer is there. So when I click, the particles will vibrate. So how many vibration for these particles? One complete vibration means, like if it is going down, then it will go up and then return back to the same place. That is called one complete vibration. So when we focus on one of the particle, so how, in a 10-second, how many times it is vibrating in 1 second, that is called frequency. So when we count the number of vibration here, in 10-second timer, it is vibrating 10 times in 10 seconds. So how many times it is vibrating in 1 second? So it will be 10 divided by 10, which is equals to 1. Because the number of the vibrations divided by the time interval, that will give us frequency. Same way, as you can see the other picture, again in a 10-second timer, more vibration, fast vibration in 1 second. As you can see in the picture. So it is vibrating 14 times in 10 seconds. So 14 vibration in 10 seconds. So 14 divided by 10, that's why the frequency is 1.4 hertz. And the last one, it's vibrating very slow. So as the particles are moving or vibrating very slow, in 10 seconds it is vibrating approximately 5 times. So 5 divided by 10, the frequency will be only 0.5 hertz. So if more vibration per second, the frequency will be high. Less vibration per second, the frequency will be low. So same way, these particles are moving up and down and they're transferring energy from one place to another. So frequency is how many waves are there in 1 second. It is denoted by a symbol F and the unit is hertz or second inverse. And frequency is reciprocal of the time period, or time period is reciprocal of frequency. The term time period means time to complete one vibration. So in this picture, as you can see, it was having 10 vibrations in 10 seconds, so we got the frequency. But how much time one vibration will take? So when we take a reciprocal, the total time divided by vibration, what we will get? We will get the time period. So the wave which is having a higher frequency, more vibration per second, will have a shorter time period. So frequency and the time period are inversely proportional to each other. These are some waves representing or showing the vibration, like from a main voltage form. The time period is 0.02 second, whereas for a tuning fork it is 0.0025 seconds, which is 2.5 millisecond. An ultrasound scanner, it is producing 10 microsecond. That's the time period, time to complete one vibration. To find the speed of the wave, speed is distance divided by time, because the wave does not accelerate in a medium, and the distance traveled by a wave in 1 second, or speed is the total distance traveled by any point from on the wave in 1 second. If we want to calculate speed, we can also calculate distance over time, or we can also use the formula, the wave equation. Speed is frequency multiplied by wavelength. So example, the diagram shows the wavelength is 8 centimeter and the time period is given. The question is, state the amplitude. What is the amplitude of this wave? What is the amplitude of the wave? So amplitude is the height, which is 2 millimeter. Then frequency means how many vibration in 1 second. So as you can see, the number of vibration, this is 1, 2, 2 point, so it's having 2.5 vibrations in how much? What is the total time? It is 1.25. So you will get 2 hertz. This is one way. Or what you can do, first find the time period, time to complete one vibration. The time period is 0.5 seconds. But we need a frequency. Frequency is reciprocal of the time period. So T is equals to 1 over F. So 1 divided by 0.5. We'll also get the same answer, which is 2 hertz. And if we need a speed, after knowing the frequency and the wavelength, speed is frequency multiplied by wavelength. Because the wavelength was in centimeter, so answer of the speed will be in centimeter per second. If wavelength was in meter, then answer will be in meter per second. A radio station broadcasts on a wavelength of 250 meters, so the wavelength lambda is given. Radio wave is having a speed 3 exponent 8. Calculate the frequency. So we'll use the formula, speed is frequency multiplied by wavelength, or frequency speed divided by wavelength. We'll get the frequency. Now, to study the properties of the wave, what we will use a ripple tank. Why we use a ripple tank? Because it is easy to produce the waves in a ripple tank. The water waves are easy to produce and we can observe them. So if we want to study the properties of the wave, we will use a ripple tank for that. This is a picture which represent or shows a ripple tank. So the water is there inside, and when these bobs are vibrating to and fro, it will produce a ripple, so we can study the properties of the wave. But what we will do, we will observe the wavefronts at the bottom, or on the screen we'll observe the wavefront. So example, first is a reflection. When the wave strikes the surface, it bounces back or it changes the direction. This property of a wave is known as reflection. Example, you have a barrier. The wave strikes the surface and it bounces back or it changes the direction. What we call that as reflection of the wave. These are the wave fronts, because instead of drawing the waves, the wave fronts represent identical points of different waves. So when we join the identical points of different waves, what we'll get the wave front. So instead of drawing the wave, we are only representing by a wave front. So wave which is reflected from the barrier, the angle of the incidence and the angle of reflection will be same. How we'll work out the angle of incidence? The ray which strike the surface, that is incident. Imaginary, which is perpendicular to the surface, that is known as normal. So when we measure this angle of incidence and angle of reflection, both will come out same, which is also known as the law of reflection. As another picture, you can see the wavefront strike the surface, and the direction of the wavefront is always perpendicular to the direction of the wave. So when they strike the surface, they bounce back. When we draw the wavefronts or show these wavefronts, so wavefronts are always perpendicular to direction of the wave, and in this example also angle of incidence will be equal to angle of reflection. The term refraction means when the wave travels from one medium to another, it changes the speed, and this property is called refraction. But how we create a two region in a ripple tank? Because in a ripple tank, so to create two regions, if this is a ripple tank, we'll place an object inside. So when we place an object inside, this will create two regions. One of the region is a deep region, greater depth, and the other one is a shallow region. When we compare the density of the water in a deep and a shallow, because in a deep relatively more space available for the particles, so relatively they are away from each other. In a shallow, the particles are close to each other, so that is having a high density. Comparatively, shallow regions having a high density compared to that of deep region. So when the wave travels from deep to shallow or shallow to deep, so it will change the speed and the wavelength. So this property of a wave traveling from one medium to another and changes its speed, we call that as refraction. Direction might change. Change in direction is not, it depend on how the wave enters from one region to another, but always there will be a change in speed. So as you can see, you're looking from the top of a ripple tank. So wave fronts which are in a deep region, they're moving faster because it's having a low density. But as they enter a shallow region, they slow down the wavelength, the distance spacing between the two successive wavefront decreases, but the direction does not change. Why the direction does not change? Because it is passing along the normal. So when it is passing along the normal, there is no change in direction. So when wave reach the shallow region, the wavelength decreases, the frequency remains same. And what you can understand from the wave equation, according to wave equation, v is equals to f lambda. So f is equals to v divided by lambda. In a deep region, maybe the speed is 10 and the wavelength is 5, so the frequency is 2 hertz. In a shallow region, the speed decreases, the wavelength also decreases, but the ratio 5 divided by 2.5, which is equals to 2 hertz. So ratio of speed and the wavelength does not change. That's why the frequency will be unchanged. When a wave is making certain angle when traveling from deep region to shallow region, so the part of the wave which is in a shallow region will travel slower, so it will lag behind. So if we show the wave front, so the part of the wave front which is in a shallow region, that will lag behind, slow down, and the wavelength will also decrease. And what we'll observe as the wave slow down, it will bend towards a normal. Again, the frequency remain unchanged, only the speed and the wavelength will decrease. As you can see in this one, the part of the wave which is in a shallow region, it lag behind or slow down, where the part of the wave which is in a deep region is moving faster. So what we'll observe there is a change in direction as the wave travel from deep region to a shallow region. Same way, it is a side view when you observe the wavelength in a deep region with a wavelength in a shallow region, so you'll find that the wavelength is also decreasing. Then diffraction. What is the meaning of a diffraction? The diffraction means spreading of the wave when it passes through the gap. So when the wave is passing through a gap, it's spread out, and we call this as diffraction. So spreading of the wave around the edges or near the, or and diffraction is maximum when the wavelength is approximately equal to the gap size. If it is too small, then there is no diffraction. So the possibilities, there are three ways the diffraction can occur for a wave. Number one, like three cases are there, three scenarios. When the gap size is too small compared to the wavelength. This is one way. Or the gap size is approximately equal to the wavelength. And maybe the gap size is larger than the wavelength. So these are the three scenarios. The gap size example is denoted by D. So here wavelength is much bigger than the gap size. Here wavelength is approximately equal to gap size, and wavelength is less than gap size. So here, if too large, then there is no diffraction, no spreading. Here, when it is approximately equal, then we'll have a maximum diffraction, so wave will spread out more. Here it will spread out, but small amount of wave will spread out. So this is maximum diffraction, this one is minimum diffraction, and the first one is no diffraction. So diffraction of the wave depends on the gap size. So if we have, because we are studying a diffraction of water waves, but this is valid for all kind of waves, diffraction can occur. We'll discuss other types of waves as well, their diffraction, but we are studying the properties or discussing the properties of the wave. So for that, we use a water waves because they're easy to produce and observe. So example, these are the waves which are passing. Then there is a gap in between. So when these wave passes through this gap, they spread out. Changes the direction. So small amount of diffraction or spreading. As you can see here, the gap size is a bit larger than the wavelength. That's why there is a small amount of diffraction. The wavelength of a wave is much smaller as compared to gap size. But if the wavelength is same size as the gap, so there will be greater amount of diffraction or greater amount of wave will spread out. We call that as a maximum diffraction. Now, what is the effect of the wavelength or the diffraction? So longer wavelength diffract more than the shorter wavelengths. If we have a longer wavelength which are passing through a gap, they diffract more as compared to shorter. And for gaps, the wavelength should be same as the gap size to get diffracted. So same thing, diffraction of the sound wave, like effect of or how the sound wave diffract. The speed of the sound wave in air is about 330, and the typical frequency which we normally produce, it's about 440 hertz. So when we find the wavelength v is equals to f lambda, the wavelength is approximately 0.75 meter, and this 0.75 meter is same as the width of the door. That is why you will find that any size of the house, you will have the same door gaps. What is the reason why you have a same door gaps about 0.75 meter or closer to that value? Because what happened, example, if a person is at position B and you are inside the room at position A, so when you produce the sound, these are the wave fronts. So when you produce a sound, your wavelength of a sound produced matches with the gap size, so the wave will spread, and a person at position B is able to hear you without looking at you because of diffraction. Same way, diffraction of the light wave. For light waves also, diffraction can also happen or occur. So what happened, like example, here is a light source and its place screen is there. Now we put a slit. So when we put a slit, what happened? The wavelength matches with the gap size, so greater spreading is there. The wave will spread out, and we call this phenomena as diffraction. Diffraction of the radio waves. Radio waves also diffract or spread out. Example, this tower is emitting out radio waves in all the direction. These are the wave fronts. So a transmitter is producing a radio waves, and this antenna is actually used to detect these radio waves. So this house is there in the shadow of some hills, like next to hills. This house is there, and the aerial on the pole is trying to improve the reception of the radio waves to receive more radio waves. So what will happen? Will the people living here be more likely to receive longer wavelengths or shorter? So what happened? As you can see, longer wavelengths, they diffract more. So as they spread out, the shorter wavelengths are hardly diffracted. But if you use a longer wavelength, they have more diffraction or greater diffraction. So a house which is located next to this hill likely to receive the signals. So hills act like a edge and cause a diffraction. So longer wavelength diffract more than the shorter wavelengths. And same way, example, it is located between the, so hill in this manner. So this is a top view. So this is very little diffraction for the shorter wavelength. But when we use a longer wavelength, what we'll observe, the top view will likely to receive the signal. So for radio broadcast, we use a longer wavelength rather than shorter wavelengths. So example, you are having a difficulty with the signal strength on your shortwave radio because, so what is the reason for that? Which one will diffract more? The longer will diffract more, so you will be able to receive the signals. Shorter will diffract, but small amount of diffraction will be there. So less likely to receive, or if we receive a signal, a small amount of signal will be received. Which of these shows rays are reflected? A, B, C or D? Which one is representing a reflection of the wave? So C is representing a reflection. So C is showing the reflection. Which one is showing the diffraction at a gap? So when it passes through a gap, it is spread out in both ways. Which one is showing a refracted ray? B is representing a refracted ray. And which one is showing a diffraction at an edge? So D is representing a diffraction at an edge. Which of these shows how a wave are reflected? Which one is showing a reflection? B is showing a reflection. Which one is showing a diffraction at a gap? So D is representing a diffraction at a gap. Which one is representing a refracted ray? And so refracted is A, and which one is showing a diffraction at an edge? So C is representing diffraction at an edge. So these are some properties of the wave. The reason why I quickly go through this part, because this is related to O levels and we already discussed these points in O levels. That was the reason why I quickly go through this part. Now the things, the extra things which are in A levels, which you have to go through. I'll explain that in another session. I'll end this session and share the recording with you.